Hello.
Yeah. Maybe since this is the first class, maybe you can try to turn on your videos so that at least I can see some faces. Yeah, if you can, that would be nice. So I can see Kinjal.
Sorry.
Okay, so if more can turn on, that would be nice. So Kinjal, Aratrika, Amlan, I can see. So most of you are at home, right?
Yes, sir.
You're attending your classes from home.
Yes, sir.
Okay, good. I also wanted to get a sense of, there are a lot of IIA students, there are JAB students, there are undergrad students in the class. So is this one of your first classes, or have you started class, did the fluids go, did you take the fluids class already?
Yes, in the morning.
Okay. And they were all, right. So Arun was also using Teams, right?
Yes.
Okay. How did that go? Was it like seamless?
Yeah, it
Or?
there was some hiccups with the writing, the notes page.
Okay. Okay.
Video.
Okay. So there are 20 people now in the class. So let's do this way. So now what I'll do is actually, so now I'll actually do it in batches. So first I'll ask the JAP students to turn on. Just a sec. I think I had an earlier link which was not quite right. So some people I wonder may be joining there. Let me actually just send a message on that channel that just a sec. Sure. Yeah, I think some people are trying to attend it in the other channel I had by mistake. Okay, so so you guys have joined the correct channel, but there are some others who I should ask to join. Okay, so now there are 25 people. Okay, sorry about that. So I was like, I had created a separate link earlier, which is not in this channel. So this is better where, the Teams meeting is part of this whole group. Anyway, we are all learning how to do things in the best possible ways. Okay, so now there are 24 people. Okay, Shrikar, Suhas, Sheikh. Okay, good. So let's do this way, okay? I don't see Ankit is here. Ankit is our TA. You can see my face. So I'll actually ask students to turn on their mics and their videos, and we'll go one by one. So maybe we can start with the JAB students turning on their videos and their mics so that at least I can know their faces and their voices. So let me see who they are. So Ritesh, I believe Ritesh, Priyanka, Harshita. Who else is the JAB student? Ritesh, who else is the JAB, is one of the JABs? Do you guys know each other?
I, I, I think 4 of us actually. Can you confirm anyone? File? I'm not sure.
Priyanka is here.
File, Priyanka, and I don't know one.
Pile, yes, MNOP. I don't see Pile here. Okay. So some people were actually confused by the other link, perhaps, but most people are at the correct place now. Yes, the guy. There is Harshita.
Sir. Yes, sir.
Can you turn on your video, please?
Sure.
And there is Payal. Payal, can you please turn on your video? So, so there are 4 JAB students, okay. I don't see Payal. Okay, good. So I can see faces. So welcome to the JAB program and this course specifically. Okay. So there are some sounds of pounding. If others can mute their video, mute their mics, that would be good. Okay, good. So you are all joining from your homes. Yes. Hopefully the internet connectivity is not too bad, and you can actually attend these classes normally. So now you can turn off your videos. Okay, good. So what about the IIA students? Can they turn on their videos? Okay. Okay. So what are your names? So I have your usernames. Sachin, is that your name?
Yes, sir. It is Sachin Raturi.
And Kuntias, what is your name?
Yes. Soumya Kuntia.
Soumya.
Yes, sir.
Okay, Soumya. And what about other IIA students?
Sir, Neeraj Rawat. This is
Neeraj, can you turn on your video, please?
yes, sir. I have.
Amalan.
Yes, sir. Yes, sir.
Okay. So there are 4. Who else?
So this is Aratrika.
Aratrika.
Amrita. Yes, Amrita.
Amrita. Okay. Who else? Danush. Okay.
Sir, this is Judhajit.
Yudhajit. Okay. And anyone else from IIA? Neeraj Rawat, I guess.
Yes, sir.
Mm-hmm.
Yes, sir. Hello, sir. I Sipra Hota.
What's your name?
Sipra Hota.
Sipra. Okay. Anyone else from IIA? No. Okay. So that's good. So who else? RRI? Anyone from Raman Research Institute?
Yes, sir. Kinjal from Raman Research Institute.
Okay. That's it. Just one person from RRI.
I think there's supposed to be 4.
Manish Kumar.
Manish Kumar.
Okay, you are also from RRI. So RRI is done, IA done. Anyone else from other institutes apart from IISc? ICTS or something else? No. Okay.
Yes, sir. ISRO.
Oh yeah, ISRO. So who are you? Bhuvana.
Bhuvana. Yeah.
Is that it, or is someone else also joining from ISRO?
There's one more girl.
So she'll perhaps.
Atulya.
Okay. Atulya. So she'll also join perhaps, from next class or something. Yeah. Or
She should have joined. I don't know.
Okay. Okay, no problem. Okay, so now who remains are the PhD, the integrated PhD students and the UG students from IISc. So IPhD students, any IPhD students from IISc? No?
So Soumya.
Soumya, okay.
Yeah.
So you're also joining from home?
Yeah.
Okay.
I'm from second year, so we have not been called yet.
Okay, good. I think you wrote to me about something. Did you write to me about something?
Maybe earlier, like at the beginning or something I wrote.
No.
Maybe. Okay, yeah.
I'm also the department.
Yeah. About this administration.
Yes. Okay.
Yeah.
Good. Okay, so what about the undergrads now? UGs? Can you turn on your cameras, please? Yes.
So I'm Yash Mehta from 4th year undergrad.
Okay, 4th year. Okay. Who else? Shrika. Kruti. Okay, Kruti, I know you. You're also from the 4th year, right?
Yeah.
And have you started working with Ajit already?
Yeah, actually it's been a month. Today I have my seminar.
Okay, good. Nice. Who else? Shrika.
And I'm Srikar.
And there's also Vishnu. Shrika, which year are you in, Shrika?
4th year.
Okay. Vishnu, you? Hi, Vishnu. Which year are you in?
Yes, sir.
You are entering 3rd year.
Yes, sir.
Okay. So, just be careful. You can actually take it later as well. So it's better if you take, other courses and then take it a little bit of thermodynamics, StatMech, little bit of ENM, advanced ENM. All these concepts will be used. A little bit of quantum mechanics. Okay. So did we leave anyone else from the UGs?
I am Harsh.
Harsh.
I am fourth year undergraduate.
Okay. Hi, Harsh.
Ramachandra, 4th year physics major.
Okay, good.
Yeah, I'm interested in condensed matter, but I wanted to just explore.
Sure. Who else? So these are all the UGs that we have. About 5-6 of you guys. Is anyone remaining? Has everyone introduced themselves? Suhas, Sheikh. I don't recall Suhas. Ritesh is there, Ramchandra, Priyanka, and Pranav, Bhamidipati. No. Okay. Roy.
Yeah, hi, I'm Kaustubh Rai.
Okay, Kaustubh. So you are
I'm UG second year.
UG second year. So there are also. So you entered second year?
Yes.
Okay, okay. I mean, this is perhaps not suitable for you, but you can.
I've been doing like my project was in astronomy, so it had like a lot of these concepts which I like went through like not very deep or in depth. So I just want to explore it a bit.
I see. You know, you can do it a little later. That's fine. You know, when you do projects, yeah, you will need some of these concepts, but if you have a little bit more physics, basic physics background, these are this course is better done then. But it's fine, you know. Okay then. So this takes. So Ankit is here. Ankit, our TA.
Yeah.
Yeah. So Ankit, maybe you can turn on your video.
It's turned on, I think.
No, I don't see you. In fact, I don't even see you somehow.
So let me redo it.
It shows a cross on your
now.
No, at least I cannot see it. Maybe others can. Not sure. Somehow your name, there is like a cross at the bottom saying offline. I don't know why. I can hear your voice.
Yeah, I can also hear you.
Okay, now we can see your face. Okay, so this is Ankit. He's a JAP student he's working in IIA. Maybe you can tell about yourself a little bit, Ankit.
Okay, so I'm Ankit Kumar. So I am a 2017 batch JAP student. So now I'm in 4th year and working in IIA with Dr. Mosmidas on interacting galaxies.
So yeah, Ankit will help us out with various things in this course, and you know, things like helping me grade homeworks and, you know, assign, you know, exams and so on. And he will also be a point of contact in the sense if there's some problem, you can always write to him or me. Both of us will be together doing all these things related to the course. Who is Rishik? Rishik? So Rishik,
hello,
yes, I don't think you told anything about yourself.
Yeah, I'm second year undergrad student.
Second year, so there are some second years also in this class. Okay, you know, as I said previously to one of your friends, that second year is a little too early. You know, it's perhaps better to take a little more physics courses and then come to it. And you will have a lot of time. Okay, good. So introductions is more or less done. So I know roughly the constitution of the class. Okay, so that part is done. So I will so one thing. So all these classes will be recorded, and I have a tendency to forget to start recording. So, you know, please remind me that, you know, start recording, please. Otherwise, you know, some of the classes may be missed. So the recording is important for people who may miss the class because of, you know, bad internet connection that day or some other reason they are not able to attend. So all these classes will be recorded and we will have live interactions. So that is the model that we are going to follow. So please, you know, if you don't see that I am recording, just remind me so that I press that button and the session is recorded. Okay? Yes? Just, you know, and how can you tell whether it is recorded? On the top left, you can see this red recording button. That should be active. That means the session is being recorded. Okay. Okay, so let me actually start. You know, I made some slides. So, you know, the class will be a mix of slides and some online, you know, writing on the whiteboard. I thought this would be more interactive than doing it in a traditional blackboard, because, you know, if I use a blackboard, I'm a little far away from the screen. Whereas if I'm speaking here, it's almost being face to face. I mean, this is the first time for me as well, teaching in this way. So I have a lot to learn how to make the best use of the platform that we have. Okay, so let me start doing. I made some slides. Today's class is more about the mechanisms and the way we are going to do it, rather than starting right away with the material. So let me start sharing the screen. Any questions before we start that? And if it will be good if people can mute their audios, because sometimes that causes disturbance. I think Pranav hasn't muted it, so I will mute it for him. Okay, so I will start the slideshow. Feel free to interrupt. This is supposed to be like a real class, so feel free to interrupt if I'm going too fast. If something is not clear, I will be happy to repeat. Okay, so I will. So how should we do it? So I will share my desktop, and you will see. Okay, so can you see my slides?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So I think I'm not going to do slideshow for some reason. In the slideshow, what happens is I cannot get that pointer. Maybe there's a way to get it. Yeah, let's see. Let me try that. Let me try and see if I can get a pointer. I think that is fine. Just this is good enough. So this is the course, PH362, Radiative Processes in Astrophysics. My name is Prateek Sharma, and I'm a faculty in the physics department here at IISc. So welcome to the class. So this is me, and this is Ankit. You already saw him, and of course we have about 25-ish students in the class, which is roughly the strength that we have normally. Around 20-25, and it's sort of a mixed class, as you saw. So there are undergraduates, JAP, Joint Astronomy Program students, PhD students, some IPhD, integrated PhD students, IIA students. So different people have different timings and preparations and so on. So to keep that diversity in mind, we have to we have to be flexible to accommodate everyone's reasonable requests, but we cannot be too flexible, otherwise someone else will have problem. So in this sort of first class, I will actually mention what are the aims of the course, what is sort of the broadly the material that we are going to cover in this course, how will it work, or the modus operandi of this course, the book or books that we are going to follow, homeworks and evaluations, and what are the expectations of this course from a student and from an instructor point of view. So the aim of this course, right? So the aim is to understand. So in astrophysics, most of the information about the systems that we are studying, right, comes through the photons or the light that we receive from these objects, like the sun, right? We cannot go and collect sample from the sun and study, right? Normally when we do experiments, we have like a full setup which is in our hand. We can play around with it and change some elements in it and do much closer inspection. Okay, whereas this is not possible in astrophysics. So most of the information that we have about astrophysical objects is through the photons that they emit. Okay, so we have to be able to interpret this light that we are receiving different astrophysical objects. And for that, we have to understand the physics of how light interacts with matter and how different signatures of that material, the physical properties are embedded in the light that we receive. Okay, so this is sort of the aim of the course, that to understand the background physics of how photons or light interacts with matter and how the physical properties of that matter are sort of embedded in the photons that we receive on Earth, right? So like, 250 years ago, before the advent of spectroscopy, people thought that we'll never be able to understand stars, in the sense of how we understand things that we can access by hands, right? People, we can understand geology really well. We can collect rocks and break them and do mass spectroscopy of those rocks and find their mineral content and various elemental composition studies and whatnot, right? But before spectroscopy, before the advent of this science of spectroscopy, people thought that we'll never be able to understand, more than the locations and the brightness of stars, right? But the whole thing sort of changed after the invention or the discovery of this science of spectroscopy, in which by looking at the light, we can understand what various substances are made up of. Okay, and as I said previously, you can stop me and unmute yourself and ask a question if you have any question in the middle. Okay, this is not like a talk that you attend. This is a class, and it better be better go in that way. Okay, so if you have any clarification, any question, anything, please interrupt. Okay, so what would be the modus operandi of this course? We have classes from 12 to 1 on Mondays and Wednesdays, and I have created this Teams. Where is Teams? I have created this Teams. How do I? This Teams team in which you guys are all participants. And so how do I? Okay. Here it is. So this is okay. So this is the team that I created. You can see, right? So this is the general channel of that Teams page that I created. So this is the general page. It's just I just send this welcome message. The classes will be conducted in this channel, the class channel. Okay, and I'll hand out the homeworks on this channel. So these different channels.
Professor?
Yes.
Please. Some of us have not been added to the team.
Right. So the people who have not been added, I will add them if you send me a request to add you guys. And what's the best way of doing it? So what I will do is actually, I guess most of you are already added, I believe, but some may not be. Just send me an email and I'll add you. Anyway, this is open to everyone to join for now. If you in a week or two, you can actually decide whether you want to officially join it. Then you can actually send it. If you in the end decide not to pursue the class for various reasons, then you can just come for 3-4 classes and after that decide whether you want to join. It's up to you. It's joining is not a big deal. If you have not joined, just send me an email and I will add you to the team. Is that okay?
Yeah, sure.
Okay. So this is yes. Any other question?
Hello.
Yes.
Yeah, you could just post the invite link in the chat box so we could just join right now.
Okay, that's nice. Yes. So this is the.
Professor,
Yes.
one note. So those of us who are not on the team cannot access the chat box.
Okay.
Don't have access to the chat box. So
okay.
Code so that we could send you a joining request.
Yes, I will actually do that. You know, one thing that I don't like is while the class is going, I don't want chats, right? You know, that distracts the participants. But what I will actually do is the suggestion that someone gave just before you, and in fact, if you interrupt and ask questions, you can actually tell your name first, so that I have like some sort of a mapping to the name, right? To the voice and names can be mapped. Normally, when you're teaching in a class, you can just see the face and you know who this person is. Here, I have to actually rely on the voice. So if when you interrupt me and ask me a question, just tell this is Pranav, and then ask the question. Okay, that will help me. Now, someone said that I can actually just share the link to this add member, get link to team. Okay, so I have copied this and I will actually post it in the chat. And I think this should be.
No, sir, the people can't access the chat. Only who are in teams can access this chat.
Oh, okay. Even you cannot see what I post. Okay.
Professor?
Yes.
I'm Vishnu.
Yes.
Instead of link, you can just post the team code. People can just join the team with the team code. It's just a number, 6-digit number.
Okay. Where do I find that? That's another thing. Manage team. Just a sec. I think this is the way to do it.
Go to settings.
Pending requests, channels, settings. Guest permissions. Allow.
Professor, there's an option called team code over there.
There's team code, the fifth option from top.
Okay, generate. Share this code so people can join the team directly. You won't get join requests. Okay, so this is, you can see it, right? I will actually copy it. You can see it, GEVS 744. So, guests won't be able to join with the team code. It says. So, but IISc people can join. So people who have IISc email account can join. Anyway, we'll actually figure this out. There is also this, just a sec. There must be settings for letting people. There must be settings for letting guests. Yes.
These members are the people who are already there.
Yes. So there must be settings somewhere to allow people to chat. Allow people who are not already on this to send chat messages.
No, they can't. You have to first add. After that, only they can.
Okay. So let me just see then. So what I'll do is just tell me your names and email ID. I'll just add right now. People who are not already on this team, can you please speak up and tell your names, email IDs?
I just typed the code for the team and joined. Like right now, I see the team with the invite code that you showed. So I can access the team now.
So you are not from IISc?
I am. I'm the second year undergraduate.
Yes, but so people who are in IISc can actually join with that code.
Oh,
People
okay.
who are not in IIC, like external people, say from IIA, who haven't already joined, will perhaps
I see.
need me to add them. So anyway, whoever wants me to add them right now, I can actually do it. In the first class, I really don't have much to present. I will show some of the other things that I prepared. But if there are people here who want me to join, add them to the students right now, they can tell me their email addresses. No? Okay, then that's fine. If you want me to add you, just email me. That perhaps is not a bad option either. Okay. Okay, then I'll close this. Let me go back to my presentation. Okay. Right. So I would like all the communication about the course to be on Teams. So if you can write messages which are visible to everyone, or you can write to me personally on chat if you want your message to be private. Okay, that is fine, but it's better to have all the communication on the team so that it's at one place. I don't have to go through my emails again and again. Okay, we'll post the homeworks and everything on team itself. That's how we'll work. What about the book? So I have actually so if you go to this Teams page, if you go to the general channel, so if you go to files here, you can actually see class materials. Okay, in this class materials, you can see the syllabus. So this is the syllabus of the course. Okay, and we are actually going to follow this book, Radiative Processes in Astrophysics by Rybicki and Lightman, very, very closely. Okay, so these are sort of so this 25 here stands for Rybicki and Lightman. So that book that we are going to follow, and this is like roughly the material that we are going to cover. So radiation transfer for 5 hours. This is chapter 1 of the book. Radiation fields. This is chapter 2 of the book. We'll spend roughly 5 hours on this, and relativistic effects and Bremsstrahlung, synchrotron emission, Compton scattering, plasma effects, and atomic structure. So this is roughly the syllabus. It's actually very well defined. You can see all these topics in the book itself. So it's a good idea to keep reading the book. Okay. Now this book, I have actually also put it there in these books. So there are two things that you can see. One is this Rybicki and Lightman. This is a PDF that I got. Don't share this PDF outside with anyone. This is not legal, but I have a e-copy of it, and I have actually the physical copy as well. So I mean, this is just for the class that I have got it. So you can actually download it from here, and this is the book. These are the authors, Rybicki and Lightman, Radiative Processes in Astrophysics. This is sort of the classic book on this subject, very commonly used in astrophysics. It's a good book. So this is the main book that we are going to follow. Then there is this other book which I have actually also put here. This is by Malcolm Longair, and this book is called High Energy Astrophysics. So this book focuses more on the high energy aspects of the subjects. That is, when you have relativistic electron emission due to relativistic particles, and interaction of cosmic rays, which are relativistic protons, with a medium, and so on. So this also sort of covers similar topics like synchrotron radiation and Bremsstrahlung and whatnot. But this does not cover radiative transfer. This says more of high energy processes, in more detail than high energy processes like Compton scattering, cosmic rays, and so on. But the main book that we are going to follow is the other one, Rybicki and Lightman. So you can actually download it from here. and put it on your laptop or whatever you're using. Okay. Anything on this?
No, sir.
Okay, good. The book is very, very important. We are going to follow the book closely. The book is beautifully written. It has the right balance of physics and astrophysics, and right balance of rigorous theory and practical examples. A lot of good homework problems. So this is about the book. I will be giving homeworks. I will give roughly 5 to 6 homeworks in this course. Okay, and a lot of these homeworks will be from Rybicki and Lightman's book, and most of them will be from Rybicki and Lightman. But I have also made some homework problems of my own, which I will put in the homeworks. So there will be about 5-6 homeworks throughout these 4 months. Okay. And I will announce the deadline. So so basically I will actually tell you what I have thought about homeworks and evaluation. You can tell me if that is fair or reasonable. So we will have, I was actually thinking, I was talking to Ankit the other day, and I was thinking that we won't grade the homeworks because it's a lot of work, 25 times 5 or 6 times 20 questions, or 15 questions every homework, or 10 questions every homework is a lot of work. So we will not grade homeworks. The homeworks do not carry any weightage. Okay, but you have to do them. Why you should do them is because, so we were actually thinking of holding like 4 exams roughly at the end of every month. So this is October. We'll have first exam at the end of October, second at the end of November, third at the end of December, and fourth in the middle of January, or roughly around the end term. So there is a lot of focus for this semester to have continuous evaluation rather than the traditional midterm final evaluation, because of the nature of the instruction that we are having this time. Okay, does that sound okay to you guys? Like, have 4 exams. So what we will do is we will make, like, we'll put the PDF of these exams. We will tell you beforehand what the day and time of this exam is. So for example, these may be like 2-hour exams. We'll send this PDF at, say, whatever, 12 o'clock or 1 o'clock in the afternoon. We'll decide the time beforehand. It will not be like random when it clashes with your other commitments. But once we decide it, we'll give it to you after within 2.5 hours. You have to scan your written worked out problems and send it back to us. That is how we are thinking, that in these 4 exams, we will give you like 2-hour exams, and you have to just scan your writing and send it back to us. We will evaluate them. And the reason you should do homeworks is because almost everything in the exams will be from homeworks. This is how we are sort of thinking. That will be a motivation for you guys to do the homeworks, because evaluation will almost be the same questions that you do on homeworks. Any questions on this, or any suggestions or concerns?
Sir, this is Kinjal. I have one question.
Yes.
So this 4 exam will be instead of the final and the midterm exam, or along with?
No. This only 4 exams we will have. So like 25% weightage each. So there is no midterm or final.
Okay.
This is the only evaluation, right? We can have quizzes and all that, but I don't like multiple choice questions or things which don't require a lot of thought. So this is what I was actually thinking, that you just have 4 exams. So a single exam does not carry a lot of weightage.
Okay.
Right?
Yes.
And it's sort of more or less continuous. So if we feel that some students are not doing okay, we do have a warning beforehand that after the first exam itself, we'll know that you better start focusing on the course. That is sort of the thinking. Is that fair?
Yeah. Yes, sir.
And most people have good enough internet connection that if we give half an hour extra for you to scan and upload, you will be able to do that, right? Everyone knows, everyone has like something like a cam scanner app or something equivalent, so that they can upload these PDFs of their written homeworks, right?
Yes, sir.
But cam scanner, I think, is banned, right?
Or whatever,
Yeah,
I'm sure there is something equivalent of it. I don't care about what the software is. Okay. So that is sort of the evaluation aspect that I am thinking of. If someone is in emergency, for example, that particular day, someone has a power cut or something, they can send it on WhatsApp, or you can just sort of take photos, send it on WhatsApp. Just, you can tell me right then and there, and we'll do something reasonable. We will be reasonable. It will not be unreasonable. Don't focus too much about grades or about exams, right? Especially the PhD students. The grades and exam results really won't matter all that much. What will matter is how you do in your PhD work, your research work. Okay, so this is all there is. So we also have some expectations that people will not like copy or help each other out in the exams. It's perfectly okay normally for you guys to talk among yourselves and clarify the concepts, but do not help out each other in the exams. Okay, that's not fair. You can talk among yourselves if you have doubt, if something is not clear, have discussions, but no copying. And I think the IISc students and the other PhD students are responsible enough that we don't have to be worried about this aspect. Is that okay?
Yes, sir.
Yes, sir.
In PhD, if you focus too much about grades, that means that something is wrong. You should not be doing PhD then. In PhD, you have to really be dedicated and immersed in the topic that you're researching. Okay, that's the way. Okay. Right. So the other thing is, we have these two classes, two class hours. We were also thinking, I was actually talking to Ankit, we can have like a weekly office hour. So the office hour is supposed to be a place where we meet for an hour, and we just discuss if you have any problems with the homework problem set or with how the course is running and so on. Is that okay? We will have we'll decide a time for that office hour, and it will be Ankit who will be attending it, but I can also come in once in a while. Does that sound good, or that's useless? Any opinions on that? Office hour. It's not compulsory. It's not compulsory for everyone to join, but if you are having some trouble, if you want to, if you are stuck in some homework problem, you can join, and you can also raise these things on the chat, on the class chat that we have on the Teams. There we'll know like a lot of people are having problems with this particular question, so we'll already be prepared by solving that question and doing it in that week's office hour. Does that sound good?
Yes, sir.
So we will decide the time and post it on Teams. Ankit, do you think some time on Friday? Friday is the day when they don't have a lot of classes. At least the physics department does not have a lot of classes, so we can choose like a Friday afternoon or evening hour for that, like 5 to 6 or 5:15 to 6:15, something like that. Ankit,
Yeah.
does that sound fine? Like 5:30 to 6:30.
Yeah, 5 to 6 we can have.
5 to see. Sometimes they have like this physics colloquium from 4 to 5, so we can have like 5:15 to 6:15.
Yeah, sure.
Is that okay with most students?
Sir?
Yes, sir.
The office hour 5:15 to 6:15, where Ankit will be there and I will be there sometimes, where we can actually talk about homework problems and other issues. Okay. So okay, 5:15 to 6:15. Yes.
So this is Yash.
Yes.
For some of our courses, we still don't have the schedule for when the TARs will be. So is it okay if we talk about it on the forum later on after the class?
It is fine. It is fine. But if you don't have any problem with 5:15 to 6:15, we can actually have that.
Yes, none so far.
Right. If there is a problem, see, you won't have classes on Friday. Most of the classes are on the rest four other days of the week. Friday, some classes may have like 1 hour engagement, but a lot of office hours can be on Friday. But yeah. Anyway, if you have any problem, just raise it on the chat. So these are the aims of the course. We'll do basic physics of radiative processes in astrophysics. We'll do a little bit of radiative transfer. So radiative transfer is the topic where you study the interaction of light and matter, basically photons and electrons, from a macroscopic point of view. Like, for example, you do hydrodynamics, right? But we know that gases are made up of atoms and molecules. But when we do a hydrodynamic treatment, we don't look at that microscopic picture, right? In the same way, in radiative transfer, we don't look at microscopic interactions between photons and material. We sort of do a coarse graining. So that's radiative transfer. So this is just the broad topics that we are going to cover. So radiative transfer includes topics such as absorption, scattering, how does some body approach black body spectrum, properties of the black body spectrum, and so on. So this is classical radiative transfer. So radiative transfer does not include effects like interference and diffraction. So this is in the ray optics limit, but you do include the effects of absorption and scattering of light. Okay, but you don't include effects of physical optics or phenomena which occur when lambda, the wavelength of the light, is of order, the scales are of order the wavelength of the light. Okay, so this is radiative transfer. Now after radiative transfer, we'll do a radiation theory. So this is advanced E&M. So you will have things like retarded potentials and how do you, if you are given collection of charges which are accelerating, how do you calculate potential and the radiation field and so on. A little bit of that. We'll do Thomson scattering. We'll do relativistic treatment of radiation theory and particle motion. So relativity will be important in this segment. So that's why I was actually saying that some of this material the beginning undergrad students may not have seen, like relativity and the stuff on radiation theory, things like retarded potential. So they may be a little underprepared on these aspects. After this thing, we'll do common mechanisms for production of radiation in astrophysics, like free emission. So Bremsstrahlung is the same as free emission. So this is a thermal emission mechanism. We'll do synchrotron emission, which is emission of radiation because of electrons gyrating around magnetic field lines. So if you have magnetic fields and relativistic electrons, such plasmas emit synchrotron radiation. We'll do Compton scattering. When you have high energy photons with h nu of order mc squared, h nu of the photon of order mec squared. So basically interaction between electrons and high energy photons can lead to the change of wavelength of the photon that's incident. So this is like a relativistic generalization of Thomson scattering. Then we'll do plasma effects, like when radiation propagates through a magnetic field, magnetized plasma, there are things, for example, Faraday rotation. We'll talk a little bit about atomic transitions, hydrogen atom, and LS coupling and fine structure lines and whatnot. We'll talk a little bit about broadening mechanisms, Doppler broadening, natural broadening, Lorentz broadening, and so on. And throughout, so this is sort of more physics of radiation, but simultaneously with this, I will give you examples of observations of various astronomical bodies. Okay, so for example, so there are like basic concepts. So now that I have sort of told you about the aims and all that, so what is the form of light that we observe? What are sort of the observations that we have? The most basic observation that we have of things are things like spectra. How much energy comes at what wavelength or frequency, right? That's the spectra. The other property for objects which are time varying, we call them light curves. So how does the flux or luminosity change with time? This thing is called a light curve. So you can look at an optical light curve or a radio light curve or an X-ray light curve of an astrophysical object. So here is an example of a light curve of a Cepheid star, delta Cepheid. Okay, so this you know how the stars are named. So Cepheus is a constellation, right? So then in that constellation, the brightest star is Alpha. So Alpha Cepheid, Beta Cepheid, Gamma Cepheid, Delta. So this is the fourth brightest star in the Cepheus constellation. Okay, and Cepheids are very, very important in astrophysics and astronomy. Okay, so what this shows is an optical light curve. So light received as a function of time from this star varies like this. It has like a nonlinear variations in luminosity as a function of time. Okay, so this is something called magnitude. Magnitude is logarithmic luminosity, right? So magnitude is proportional to log of luminosity. This is absolute magnitude. So these things you will actually learn in your fundamentals of astrophysics course. Things like magnitude, apparent magnitude, and absolute magnitude. But anyway, so for now, let me just show these examples. So this is a Cepheid star. Now this is a light curve, again absolute magnitude, which means luminosity as a function of time for different types of supernova explosions. So there are type 1As, 1Bs, 1Cs, type 2B, 2L. Don't have to go what these things are, but this is an example of a light curve. Suddenly there is a rise in light coming from some star, and then it sort of decays over a time scale of months. So this is 60 days since peak, months to years. Okay, so these are things like light curves. What about other things? So you have things like spectra. So this is how light varies with time. Like for example, if you look at the sun, it does not really have a lot of variability in optical, right? Every day the sun emits more or less the same optical luminosity. Otherwise life on Earth would be very, very different from what it is now, right? Earth is not, the sun is not very variable in terms of its optical light. It is variable in radio and in X-rays, but not in optical, where most of the light comes from in the sun. So these are light curves. What about spectra? Spectrum means basically it's like a prism, right? If you take a prism and if you shine white light through it, the light gets split into different wavelengths, right? So so basically this, you want to know how much light is coming at what wavelengths from these different astrophysical bodies. So for example, these are spectra from some stars, and these are the stellar types. So going up here, O stars, B stars, A stars, F, G, K, and M stars. O stars are the most massive and the bluest stars, and M stars are the smallest and the reddest stars. So you can actually see all the stellar spectra have these characteristic absorption features, right? You have these absorption lines. Okay, so the question is, how do these absorption lines form in stellar spectra? Right. So here you can actually see in the background, you must have read that stars are close to black bodies. So you can actually see the background black body spectrum. So O star is blue, so it peaks. So its luminosity or its spectrum peaks in the UV. So this is 400 nanometers. This is UV, right? The sun is a G type star, right? So this is a G star spectrum. You see, its spectrum peaks in the optical, right? Like close to 500 nanometers or 5,000 angstrom. So there is a background black body, but on top of that black body you have these absorption lines, which tell you about the composition and temperature of these stars. This is another way of looking at the same thing. Here you are actually shown the colors. So the x-axis again here is wavelength. So you go towards the longer wavelength on the right. So red, this is shorter wavelength on the left. And the brightness shows how much power there is. So you can actually see a trend of brightness being moving to the left or lower wavelengths as you go from M stars to O stars. It's the same actually. This is the same as this, except here we are showing the intensity by color. Here the intensity is not really shown, it's not quite shown. I mean, it's shown, but they are sort of shifted with respect to each other. But this is how actually, if you take a prism and do this, you will actually see these, right? You see these background continuum light, but on top of that light, you see these lines, dark lines, right? You can see the dark lines. These dark lines are these absorption features, right? Even in the case of the sun, when people started looking at the prism light from the sun, they noticed these absorption features, right? And in the case of the sun, these are called the Fraunhofer lines. These are very famous lines, and these tell us about what the sun is made up of and what the temperature of the sun is. Okay, so this is from stars. Similarly, we receive light from things called AGN, active galactic nuclei. Things called quasars. So I mean, these are just examples that I'm giving. As I said, the main focus of the course will be on the physics of interaction between matter and radiation, but I will actually give examples from astrophysics, because that is what you will deal with eventually. This is where you will apply your knowledge. So there are things called active galactic nuclei in astrophysics. These are supermassive black holes at the centers of most galaxies, which are powered by accretion of matter onto these black holes. Sometimes they have these radio jets, and there is like a whole phenomenon built around how an AGN looks like. So depending on where an observer is looking at, you can have different observational appearance of these AGN. So we'll not really get into detail of all this right now. Okay, so we will actually do all this in the next class. So I will actually conclude. So any questions about anything that I covered? So today I really didn't use that writing pad, but this course will not just be slideshows. It will have a lot of writing when we actually start doing the material. Okay, so I actually myself like the classroom, the blackboard teaching more than this, but we will actually get to that. Any questions, anything before we end the class? No.
Yes, sir. When you showed the AGN, there were this radio silent parts. Why were they like that?
Okay, so what I was actually thinking is I'll actually do that in the next class, but since you asked the question, right, so Right, so sometimes these AGN have these jets which emit in radio, but not all times, right? So on this side, it's an example where you don't have radio emission coming out. We still don't quite understand why some AGN are radio quiet and why are they radio loud. It has to do with the accretion physics and magnetic fields, but this is an observational fact. Some of the AGN show radio and some don't. The ones which don't show radio are called radio quiet QSOs, quasi-stellar objects. Okay, and the ones which show radio are called radio loud. So if you are looking at the jet, so this is a radio jet which emits radio because of relativistic electrons. If the line of sight of this jet is towards you, you can actually also see gamma ray emission, and these things are called BL-LAC or blazar objects. So there's a whole phenomenology associated with this. These AGN are very, very tiny in terms of spatial extent. So none of the AGN can be resolved. You cannot like see this by a telescope. But what you see are spectra, and the interpretation of those spectra is the most natural if you assume something like this. So this picture is an artist's impression, which is obtained from like abundance of various AGN types and from their observational properties. We'll actually we'll discuss this later. For now, this, your question was about radio loudness, and this is just an observational fact.
If it has something to do with the jets also, like radio quiet are not jet. I mean, they don't have jets. Or
most things which have jets also show radio emission.
Okay.
Sometimes you don't see both jets or radio emission. So jets are these narrow outflows coming out of these supermassive black holes. These are very, very common, but about 10% or so also don't show any of this. This is just an observational fact. Okay. Anything else? So you guys can check if you can download the book, and yes.
Yeah, I'm Ritesh. So I'm asking about the same picture. So what are those violet blobs around the AGN?
So you're really getting into the details of all this. So this is sort of the picture that we have built based on observations of AGN, right? So if you're looking from here, okay, there is an obscuring dust torus which is shown here in orange. So you cannot see the inner regions of it. So these are called type 2 AGN, which are obscured. So the central black hole and the very high energy region around it is obscured. So these black dots are just gas electrons. This is sort of like a corona. These are clouds. These violet circles are sort of clouds of cooler material or denser material. These are inferred from the spectra of AGN. Okay, so this whole cartoon is assembled based on the spectral properties of the AGN that you observe. Some of them show very broad lines. So there are these broad line regions. Broad line clouds are very near the black hole because there the velocities of the matter is very, very high. Whereas if you're far away, the velocity is smaller because the gravitational potential depth is lower. Okay, so this is a whole phenomenology for AGN, but we really don't want to get into that in this course. Okay. Anything else? Please download the book and start reading the book. What I will actually do is also mention every week. These are the sort of sections that we have covered like for example, before today's class, I would post, we will cover sections 1.1, 1.2, 1.3 from R and L, so that you guys know what we are doing in the class. And it's important in this present setup to study on your own, because doing classes online is not the most ideal way of doing them. Okay. Any final questions? If not, we'll post material on the channel.
Hey, Professor, this is Suhas.
What is your name?
Suhas.
Suhas. Okay.
Professor, I'm not able to access the books, the PDF
Yes.
books, as in they're not appearing in the Teams for me.
Oh, they're not appearing.
Are they in the class material section, in the book section?
No, it's in general.
Go to general.
Oh, okay.
Go to files.
Yeah, I went into the class materials thing.
Class materials, there is
and
books.
Then the books, they're not appearing.
Oh.
I'll try refreshing once again.
Yeah, I think you may need to refresh. Others, some other people can access it, right?
Oh, I can.
Okay. People from outside IISc can also access them.
Yes, sir.
IIA folks can access.
Yes, sir.
I think it is accessible to everyone. Okay. Any other questions on how we are planning to conduct this course? No. Okay then. Thanks a lot. It was very nice meeting you all. Hopefully you will have a good time. And as I said that this is not the most ideal way of conducting classes, but we can actually do very well. The key thing is to communicate. If something is not, when we are doing one-on-one classes, at the end a lot of students stay back and tell like this is not going fine, or we are having difficulties with that. So use the communication channels that technology has enabled. So you can post, you can tell me individually on chat that this is something that I don't like, or anything. Basically communicating is important. Don't communicate after the problem has worsened. Okay, that will be the key. Okay, then I will end the session. And also remember, please remind me to start and stop recording, because we don't want to miss lectures. All lectures must be recorded so that they are available to people. Okay then, have a nice week ahead. And have a good time with other courses. I will stop recording and I'll end the meeting.